Welcome back again. We spoke in the last lecture about taking the derivative of something, this a here. This could be velocity, this could be the acceleration of a particle, or position, or displacement. Position we called r. But anyway, we talked last time about taking derivatives, and in the basic 202 dynamics approach, usually the unit vectors, I, j, and k, those are the axes of the coordinate system, those are usually fixed in space. And so taking the derivative is just taking the derivative of whatever is in front of those unit vectors. So it's really simple. In this class, we'll find it really helpful sometimes to attach our moving reference frame to a body. So for example, say this wheel is spinning at a rate omega. We might attach the ijk coordinate system to that, and then r could be a vector relative to that coordinate system. One fun example of this that we'll talk about soon is any measurement that we take on the Earth. Right? The Earth is a spinning ball, and we have a coordinate system attached to that ball with north, south, east, west, or various descriptors, or latitude and longitude. And when we talk about the position of something on the Earth, this could still be a dynamic quantity. And so to be able to figure out the absolute velocity of something, we need to know how to take the derivative of a vector when the vector itself, the coordinate system itself, is rotating. So as a first step towards that, let's just look at a basic case where we have the vector a here, and we want to find the derivative of a with respect to time. And so we go back and we use the chain rule that you all remember from math, hopefully, which says that first we take the derivative of the first part times the second, then the first part times the derivative of the second. All right? So the first part, this is just like what we do in 202, simple dynamics. And this second part now, we need to think about what that means. So if we go to the picture, if we have a vector A, EA is a unit vector that points along the vector. So, in a simple case where we have I and j unit vectors, and we had something of length L here, and a position vector there would just be L in the I direction, right? So anyway, in the same sense, EA is just an arbitrary unit vector that points along the axis of the vector. And if we look at what happens when this vector moves, similar to what we did last time with rotations and things, but as we go to a new position, we'll see that the vector has to reorient itself. Or in other words, the EA vector there, if I just translate that over, has to change by some delta EA to end up in this new position. And so the derivative of the vector mathematically is the limit of this new vector minus the original over delta t, or it ends up just being in the direction of delta EA. So all of that is a lot of math just to say that the only direction in which the vector can change is the direction of the vector comes purely from the change in the unit vector. Okay, so we'll have to dive a little deeper into this onto the next slide. If we construct this and we start to look at things, and remember that EA is a unit vector, so it always has unit length. So, and this is also a unit vector, so it also has unit length. So you're starting to see that these kind of have to be on a circle. And so we can work out that EA has to be perpendicular, or EA dot has to be perpendicular to EA. So if we have a vector along the axis and another vector that's perpendicular, there's a 90-degree angle there, then EA dot has to be in that perpendicular direction because, you know, it has a constant length, so it has to be tangent. EA dot has to be, or delta EA has to be tangent to that circle in the limit. So if we take all of that into account, then we can write that the derivative of our vector has a component along the axis of the original vector that has to do with how the length or how the magnitude of the vector is changing. And remember in our other case we had Li, so this would be like the change in the length of the vector. And then we also have a component that has to do with the rotation rate of the vector, and that one is purely in the normal direction. And if we want, we could repeat the process for the En unit vector. And if we find its derivative, it ends up being in the direction Ea. So the derivative of a vector is always in a direction perpendicular to the vector. All right, and that one follows fairly easily from what we just did. So mathematically, it's a little easier to define this using a cross product. And the way we do that is we remember that a cross product gives us a vector perpendicular to the two vectors involved, and according to a right-hand rule. So in this example, if we defined theta dot by the right-hand rule, that would be a vector going into the page, and theta dot, then a vector into the page crossed into A. Using the right-hand rule, we'd have to have our fingers pointed down, thumb pointed this way, and can't really draw the fingers pointing down very well. But anyway, the cross product of those two would give us a vector En, and it would have the magnitude theta dot. So this is the way we'll use this in this class. We'll use this formula. So this is a very important formula, and you want to learn that, and we'll use that in lots of different examples here. So you can read the book if you want to see the derivation in general and rigorously done, but hopefully what we've covered already is enough for you to get a feel of where this comes from. So the important thing here is that omega A, this is the angular velocity of the vector A, or usually what we do is we think of an XYZ coordinate system that the vector is riding on. And we use that, so whenever that omega comes up, we need to remember that that's what that's for. And this will again allow us to later take the derivatives and moving reference frames, so we can do things like understand how the velocity of an airplane, how its angular velocity might be influenced by the fact that it's flying relative to the Earth, which is also spinning and translating, and exciting things like that. So basically, what we'll do to find angular velocity and angular acceleration all boils down to what's on this one slide. The angular velocity is just a sum of all of the different rates that the body can go through, all the different spins that are going on. And each one has a unit vector that defines the axis that that spin is happening about. And it's very important we pick one such that this is always true. So we need a unit vector that's always pointing on the axis. We'll see in the next example exactly how that works. And then to get the angular acceleration, we just take the derivative, remembering that the derivative of a vector is the derivative of the first part plus omega cross the vector itself. So this is the exact same as the formula we just had on the other page, omega A cross A. So that's all that we have to do. And yeah, emphasizing again, omega is the angular velocity of the coordinate system to which the unit vector is attached. So absolutely, we have to remember what that is. We'll see once we start working problems, we'll have a lot of different rates, a lot of things moving, spinning in every possible direction. So we need to keep in mind what this is for this to make sense. All right, so let's revisit this example now using this approach. And again, this is the approach we'll use for 95% of the problems in this class. And so let's see how we would do this now that we know how to take the derivative of a vector. So again, we have a table, and it's spinning at a rate omega, and it's also increasing at a rate omega dot that's 10 radians per second squared. And then on this platform we have a motor spinning at a rate phi dot, and this one is increasing at a rate phi double dot. So we're asked what are the angular velocity and angular acceleration vectors of the motor with respect to an XYZ frame that we have right there. So let's go ahead and work this out. So the first step is to write the angular velocity as a summation of rotations, with each having its own axis. And then we'll take the derivative. So let's just go ahead and take this first step. So omega has 2 rotations in this case. We have capital omega, and that one, as this wheel spins, that one is happening in the E capital omega direction, we could say, or in this case, the z-axis is always pointed upward, so that we can call that the k direction. Now, I guess it might help to specify. Actually, let's go ahead and use the notation we like in this class. So we're told that this XYZ frame is fixed. So I'm going to use the notation the book uses. We're going to call that capital I, capital J, capital K. So I'm going to call this the capital K direction. And then we have a second rate, phi dot, and that one is about an axis that's moving. So for now, I'm just going to call that E phi. All right. So this is our general description of omega, and this is always true. E phi is going to move. This then has to move with the turntable, so that it always stays aligned with the axis of the motor. And if that's the case, then this is a generally true expression, or it's true at any instant in time. We'll see in a minute that we'll write out, well, let's just do it right now just to contrast. So we could also write this in the ijk coordinate system. If we drew a picture, we would see, well, the first part is already in the ijk coordinate system. And that second term, this, to get this, we would need a cosine of theta in the capital I. So we'd need to come out this way and then up that way, and plus a sine theta in the capital J. Right, so this one you don't want to take the derivative of, because this one is not generally true. So that was the 202 approach that we took last time. So anyway, this expression is generally valid, so we can take the derivative. So we'll say that alpha is just the derivative of d omega dt. So that will be that will be omega dot now in the capital K, and plus omega times the derivative of the k unit vector, but k is a fixed unit vector, so that's obviously going to be 0. And then we need to add in the second term, plus phi double dot e phi plus phi dot, and now we need the derivative of the e phi unit vector, and that's where we'll use our formula. So we're going to need to define the rotation rate that unit vector is, of a reference frame that unit vector is attached to, and cross that with e phi. So let's go ahead and do that in one more step. What would the rotation rate of that unit vector be? Well, we said it's moving with the turntable, and the turntable is rotating with capital Omega. So omega A would just be capital Omega in the k direction. All right, so let's plug that all in and do a little bit more math there. So what we had there tells us that alpha is equal to capital Omega in the k direction plus, actually that term was 0, plus phi double dot e phi plus phi dot times omega in the k direction crossed into e phi. Okay, now to be able to evaluate that cross product, we need to put these in the same coordinate system. Now, physically, if we wanted to evaluate it using the right-hand rule, we would point our fingers up this way, cross them into e phi. And so, physically, we know that this vector should point in this direction. It should be in the ij plane, and it would have to be perpendicular here. And so physically, we could kind of work out what that is. Mathematically, what we'll do, since we want the final answer in ijk, is we'll write e phi out in ijk coordinates. And we'll need a picture. I did this by inspection a second ago, but let's just draw out the picture to be complete here. So we had a little picture that said that the e phi unit vector would be rotated at an angle theta from the I-axis, right? And towards the j-axis there. So looking at that picture, we get that that's a cosine of theta in the I plus a sine theta in the j. So again, remember we have a 1 here. This length here would have to be cosine theta, and this length here would have to be sine theta. All right, so plugging all of that in, we can now work this out. Omega in the k, double dot e phi, and then we have phi dot times omega, and then the first term here would be a cosine theta with a k crossed into I. So sometimes I'll draw a little axis here to help me. So k crossed into I, that'll just be j. And then we're going to have another term that's also phi dot omega dot. Actually, let's just write it this way. The second term that has a sine theta, that one's going to be k crossed into j. So when we do that cross product, we get something pointed in this direction. So that has to be a minus I unit vector. All right, so we can plug all of this in, and we probably also want to write this E phi in those coordinates. So when we plug all of this in, we're going to get a component that has a negative phi dot omega sine theta. That was this component here in the I direction. We're going to add to that a phi double dot component cosine theta in the I direction. That came from here. So all of that is in I. We'll also have in J phi dot omega cosine theta plus phi double dot sine theta. So all of that's in the J. And then last of all, we'll have capital, oops, sorry, this was a typo from earlier. We should have had a dot on that. Capital omega dot in the K. All right, so there's our answer. So that's how we work it out this way. We should, if we went and compared this with what we got last time, we should get the same answer. And I guess I will say it's a little unusual to do this problem and to go to the fixed unit vectors, to go to the fixed coordinate system. In a lot of the cases that we're going to do, we're actually going to want the answer to be in a rotating coordinate system that's aligned with one of the bodies that we have. So, but anyway, that's the process. In our next lecture, we'll do a couple more examples and talk about solving some other problems and some of the strategy that you can use.